welcome to the MEMS workshop with Comsol. So my name is Siva Hariharan. I'm your account manager for Michigan. So in terms of any questions about Comsol in general, I'll be your first point of contact. So we had the intro session this morning. I don't know how many people showed up for the intro session. But today afternoon, we have the application-specific workshop, which is going to be on micro-electromechanical systems. And I'd like to introduce my colleague here. His name is Chandan Kumar, and he'll be giving a presentation on MEMS.
Thank you, Siva, for the introduction. My name is Chandan, and I'm an applications engineer in the Burlington office in Massachusetts. I've been working for Comsol for the past 4 years. My primary area of expertise is in structural mechanics, but I've managed to gather some other low-hanging fruits for during the course of 4 years. I first came to know about Comsol during my research at Penn State University. I was working on self-assembly of quantum dots, and this seemed to be the only commercially available package that in its true sense could perform multi-scale simulations. Say, for example, solving for one physics on the boundary of a particular geometry. In my case, it was surface diffusion. And coupling it with another physics on the volume. In my case, it was structural dynamics. And be able to apply boundary conditions on a boundary that keeps constantly changing shape or moving. So I was able to use Comsol at the time. We didn't have that many features, but one of the powerful interfaces, equation-based modeling, I was able to use that to suit my research needs. This workshop here is to basically in one line tell you what is in the MEMS module in Comsol. So what are the interfaces? What are the types of analysis you can do? So we'll focus on those. A general outline. First, I'll introduce to you the interfaces within the MEMS module. And then we'll talk about these topics: electromechanics, structural mechanics, within electromechanics, electrical features within electromechanics, and then structural mechanics standalone, damping mechanisms, RF MEMS, thermal MEMS, piezoelectric devices, and then just few application examples. But during the course of these discussions, I will also demonstrate few example models that specifically are related to electromechanics. We'll set up some static and eigenfrequency or frequency response type of problems, and also a problem in the area of piezoelectricity. So you get a feel of how to use the interface within the MEMS module, and also a bit about two of the most important applications that the MEMS module is currently being used for. This is the product chart. I'm not going to explain the whole product chart, but just want to point out the MEMS module there contains most interfaces for modeling of MEMS devices. However, many of your applications will be multi-physics in that you may need to borrow features from other modules like AC, DC, RF, microfluidics. Acoustics is one important one that shows up. So those could be also part of your multi-physics model if needed. MEMS as such is a combination of electrical, structural, thin film flow, and thermal aspects within Comsol. And in this slide, I'm showing you an overview of all the interfaces that are available in Comsol when you have the MEMS module. So the first two interfaces highlighted here are with respect to electrical currents or electrical modeling, electrical currents, electrostatics, electrical circuit. For electrical circuits, you can either make the electrical circuit within Comsol, or you can import a netlist, a SPICE netlist. Then you have an interface for modeling piezoelectric devices. I'll discuss in details later on what piezoelectricity means and what kind of analysis can we do. Extended structural mechanics capabilities. The Comsol multiphysics base package itself has some structural mechanics capabilities, but those are extended in the MEMS module in its ability to handle large deformation and handle contact, buckling, viscoelasticity. Electromechanics interface to model electrostatic actuation. Then there are a couple of interfaces to model damping due to fluid flow. And the fluid flow can only be on the surface, as in thin film of gas or a thin film of fluid. Or you can have a bulk fluid flow that can cause damping, and that is fluid structure interaction. So those are two separate interfaces. Then you have a thermoelasticity interface for thermoelastic damping, which is basically losses introduced due to heat conduction when a material is subjected to local compression and local expansion. Piezo resistance, it's somewhat similar to piezoelectricity, but not quite. I'll explain that later on as well. There are interfaces for modeling thermal stresses, Joule heating, thermal stresses and Joule heating together. So now we'll start with specific topics, starting with electromechanics, and then I'll demonstrate a few models in electromechanics. So electromechanics means electrostatic actuation of the MEMS devices. Physics-wide, it includes three types of physics: electrostatics, something we call moving mesh, which I'll explain later on, and then structural mechanics. And the figure here just shows a cantilever beam with an applied bias, and there's air around it. You apply electrical potential difference to this beam, and then the beam bends by first you calculate electrostatic forces, which causes the beam to bend. Physics-wise, I'll break it up into each physics at a time. So if you have a beam, it could be any length, width. Usually these are high aspect ratio structures. And you apply a potential difference across the gap from the ground plane. And the first thing that you need to solve for is electrostatics, not just around the beam, but within the beam as well. And all parts of this problem is computed using the finite element method. After you solve for the electrical potential difference, you can calculate the Maxwell stress tensor, or the electrostatic forces exerted on that beam. Those forces will be applied to the structural mechanics part of the problem, so that acts as a boundary condition for structural mechanics, causing the beam to bend. You have to account for large deformation if it's a high aspect ratio structure and the deformation is large. But as the beam bends, it narrows down the gap, and so the domain of air, the regime has changed. So you have to recalculate everything. You have to recalculate the force, you have to recalculate electrical potential, because the domain within which we're doing electrostatic calculation has changed. So that's, in summary, tells you what is the basic physics involved in electromechanics actuation. What about the interface itself? The interface itself is shown in this slide here, electromechanics. Now it has several sub-branches here. I'll highlight some of the important ones. First, with regards to structural mechanics, it has structural mechanics boundary conditions that the regular structural mechanics interface has. But it has some other boundary conditions or advanced boundary conditions, like thin elastic layers, which is used to model very thin layer sandwich between two structures. Think of it as a glue or adhesive. You can also model thin film damping. So basically, if there's a thin film on top of a structure of gas or a fluid, you can use this thin film damping as a boundary condition to model that damping. The electromechanic interface that is highlighted in this slide, that models electrostatic forces that are applied to the solid. It also models how the gap changes as the solid deforms. Linear elastic dielectric, that models the electric field within the linear elastic solid. It also models structural mechanics of the solid, so that's why it's linear elastic dielectric. If the field inside the dielectric or the solid is not important to you, you do not need to solve for the electric field inside the solid. So in that case, you would be using just a solid mechanics model for the solid in your model that is bending. It could be, it can be a linear model, it could be viscoelastic. There is no predefined interface for a hyperelastic solid within the electromechanics module interface, but you could also make the solids hyperelastic, but rarely does it happen in the MEMS modeling that you need a hyperelastic solid. You can account for arbitrary forces like gravity or force due to some structure rotating. These forces can be accounted for in the body load. There are interfaces for modeling damping. You can model damping explicitly, or you can model damping implicitly. So explicitly meaning you're not telling where the damping is exactly coming from. You just know there is damping and what parameters define the amount of damping. So explicitly, there are two forms of damping: Rayleigh damping, that is viscous damping, or loss factor damping, that is material damping or structural damping due to frictional forces within the material. You can model objects that are infinite in length or width or size, but you do not want to model the infinite size of that object. Therefore, you truncate the object and then model the rest of it using a special condition called perfectly matched layer. If you're doing a frequency domain analysis, meaning you're analyzing frequency response or you're calculating resonance frequency. This is also used to model calculate quality factor. Infinite element is another feature that is available when you do stationary models. So similarly, when you have an object that is infinite in size, but you do not want to model the infinity, you truncate the object and then you use infinite elements. But that's only for stationary models. Perfectly matched layer for frequency response type of calculations. Electrical features. Within electrical features, the first thing you'll notice is something called moving mesh that is highlighted here as free deformation 1. So that calculates how the gap changes as the solid deforms. Then you have a full range of electrical boundary conditions that include floating potentials, ground, terminals, also special boundary conditions like contact impedance, dielectric shielding. There is a terminal boundary condition that allows you to connect your finite element model to electrical circuit. So you can either use a terminal boundary condition to directly apply voltage or current, or you can connect it to a circuit which in turn may have other lumped parameters like a voltage source, capacitor, resistor, inductor, whatsoever. It also outputs lumped parameters like capacitance, impedance, resistance, depending on what kind of analysis you're performing. Similar to the structural features, it has infinite elements. Infinite elements allows you to capture the effect of the electric field at infinity. I already talked about the terminal boundary conditions, so I'll skip that. Harmonic perturbation that is highlighted in this slide underneath this terminal 1 boundary condition, that is something used to perturb a DC bias. So first, let's say you apply a DC bias, electrical potential, and then you want to superimpose on top of that a AC perturbation. So it's basically a combination of the DC and the AC perturbation. That is achieved by this special feature called harmonic perturbation. And it actually relates to effects well known as spring softening or stress stiffening. Spring softening happens in electromechanical devices when the solid or the linear dielectric solid bends, it narrows down the gap. The forces therefore increase in magnitude because the gap is now narrower. That's called spring softening. Stress stiffening is related to the material itself bending. The resistance to bending increases as it bends even more, and that's called stress stiffening. Those are achieved by this feature, harmonic perturbation, in addition to a DC bias. In terms of study types, you can do stationary. So by stationary, I mean you can calculate the effect of a DC bias to the electromechanical device. Or you can also calculate the pull-in voltage. Pull-in voltage is the voltage required for the snapping of the resonator in an electromechanical device. So if you keep increasing the voltage, the resonator will keep deforming until a critical voltage is reached, at which it becomes very unstable and it snaps, or there is buckling or impact type of contact. Transient or time-dependent analysis, that can be used to calculate the transient response of such a resonator with increasing voltage, for example. There are two types of frequency domain analysis. One is pre-stressed frequency domain analysis or pre-stressed frequency response. Pre-stressed means that you have a DC bias, and then you, on top of that, you're applying a AC perturbation. So it's already stressed because of the DC bias, and then on top of that, you're doing a frequency response analysis, which is different from just frequency response analysis. Similarly, pre-stress eigenfrequency calculations, which basically means that if you do a calculation without pre-stress or without DC bias, and a calculation with pre-stress or with DC bias, you'll notice that the resonance frequencies will change or shift. That's because of the DC bias or the effect of the stationary field within the solid or the material around the solid, the fluid. So there are a couple of examples in the model library that tell you how to model a resonator, and they'll go through every step. That is, first calculate the DC bias, then calculate the resonance frequencies, then calculate the frequency response, and then calculate the pull-in voltage, the voltage required for the structure to collapse. I will set up and show one such 2D model, and we'll go through some of these analysis. As to be specific, the stationary DC field, and secondly, we'll do a harmonic analysis or frequency response analysis, and we also do a pull-in analysis in which you find the critical voltage for the collapse of the resonator. So you can follow me if you have Comsol installed, but if in case you miss a step or two, don't worry about it. It's all documented. I can point it to you later on. But I'll try to keep it as slow as possible within the time constraints we have. So we'll load a geometry that's from within Comsol's model library. And if you open Comsol, the first step here is to choose the space dimension. We will model this in 2D. You'll see a corresponding 3D example in the model library. So I choose 2D by clicking on it, and then I click on this blue arrow named Next. The electromechanics interface is within this structural mechanics branch. So you have to expand this structural mechanics branch and then click on electromechanics. After you click on electromechanics, you have to click on this blue arrow called Next. And we'll first start with a stationary analysis. So we'll click on stationary. And this time, we'll click on this flag button called Finish. The next step is to either draw the geometry or import the geometry. So we will import a geometry. First, I'll change the length unit of the geometry from meters to microns. So we'll click on the length unit option and change it to microns. And then we'll import the geometry. To import the geometry, you have to right-click on the geometry and choose Import. Click on the Browse button to look for the geometry file. If you have Comsol installed, it will be in the installation folder. So by default, Comsol will be installed in your C drive. And in C drive, Program Files, Comsol 43B, Models, and then we'll look for the MEMS module. MEMS module, actuators, and the file we are looking for is biased resonator 2D. So it's within Comsol's installation folder, Models, MEMS module, actuators. So we'll click on Open, and then click on Import. This has a high aspect ratio, so not everything will be visible right away because they're very thin structures here. So what we can do here to look at the geometry as a whole and make it easier is expand this View 1 option and then click on Axis. And here you will uncheck the Preserve Aspect Ratio option. This is just for viewing purpose. And then click on this Apply button that you see up at the top left of the middle window, which is also called the Settings window. So this blue arrow here, Apply. You'll see it shrinks in size. Now, to be able to get the geometry as a whole in this GUI or this graphics window, you can click on this Zoom Extends button, which shows up as a toolbar on top of this graphics window. So now you're seeing a compressed and shape of this geometry so you can clearly see what are the boundaries within this geometry. I'll tell you more about the electromechanical device as we model, so you'll know what are the materials within here. It's basically a resonator, and there's a dielectric, and there's a substrate, and then you have air around it. The second thing we'll do here is define a global variable. So we'll use a global parameter. We'll define a electrical potential that we'll use for DC bias, to apply a bias. So we'll right-click on this global definitions and choose parameters. In parameters, you can define all the parameter name and what is its value along with units. So here we'll just put in any user-defined name. So I'm going to choose a name capital V, small d, C. You can choose whatever name you like. And then in expression, I'm going to put in 35 volts. So 35. And then with open square bracket, capital V for volts, and close square brackets. It might be hard to see, so I'm going to use this magnifier here so you can see what I'm typing there. It's just capital V, DC, 35 volts within square brackets. OK, I'll get rid of the magnifier for now. Now we'll assign some selections. Selections is a concept necessary or very useful to model complicated physics where you have to select too many things at once. You can group them and name them something. So we'll right-click on definitions and choose selections and choose explicit. By choosing explicit, we want to create a selection of all the resonator volumes. So we'll pick one by one what are the volumes that correspond to the resonator in this geometry. This resonator is a polysilicon resonator. So we'll click on these volumes that you'll see. OK, I think we have a graphics issue here. I'm going to save this file. And change some of the graphics options here. So the idea of selections is to first select all the domains you're interested in, group them into one name so that you don't have to keep selecting them again and again. And then you can also create subgroups of the selection groups that you have already made. So I'll show you how to do that as well. I will open up the file that I left or saved. OK. Now I should be able to select these domains. So I'll select this domain. The procedure for selecting something in Comsol is a two-step process. First step is to click on that particular domain so that it turns pink. And the second step is to right-click anywhere in this graphic screen so that you select it. So I select that, and then we will select this domain here. So domains 5, 6, and 9. So these correspond to the resonator made of polysilicon. We can rename this selection. I'll right-click on explicit 1 and just rename them as resonator. R-E-S-O-N-A-T-O-R. Now, let's say if I wanted to select all the boundaries exterior to this resonator, that is saying creating a subgroup of the selection group, then I can do that by right-clicking on definitions, choosing selections, and choosing a feature called adjacent. This allows me to select all the exterior boundaries of my existing selection. So I'll choose adjacent, then click on this add button in adjacent, choose resonator, and you'll see right away that will select all the exterior boundaries here. So I didn't have to go specifically pick each boundary one by one. I saved time by doing this. And I can rename this selection by right-clicking on it and choosing rename, choose resonator boundaries for name. Similarly, we have to make one more selection. So we'll right-click on definitions again, choose selections, and then click on explicit. This time we're going to choose a driving electrode. So click on this explicit in selections, and then click on this domain here beneath that resonator right in the middle. So again, it's a two-step process. First, you click on it so that it turns pink, and then you right-click anywhere on the graphics screen so it turns blue. We'll rename this selection as well, call it the drive electrode. And then we'll again select the exterior boundaries of this particular electrode by the same process again, right-click on definitions, choose selections, choose adjacent. After you choose adjacent, you can click on this plus sign beneath this selection box. And then choose the name drive electrode for the second selection. And that automatically picks up the sides or the boundaries of the particular selection. You can rename it if you want. I'll just rename it quickly. Drive electrode boundaries. And that will help a lot in assigning boundary conditions and other conditions here, the physics itself. The next step is to assign material properties here. So we will right-click on this materials branch and choose Open Materials Browser. And here we will expand the MEMS folder that appears here. So expand the MEMS folder, and then expand the semiconductor folder to choose polysilicon. By choose, I mean click on it, and then right-click on polysilicon, and choose the option Add Material to Model. So one more time, you would right-click on Materials, choose Open Material Browser, then you expand the MEMS folder, then you expand the semiconductors folder, click on polysilicon, then right-click on polysilicon, and choose Add Material to Model. By default, it assigns everything as polysilicon, which is not something we would like, so we are going to clear it. And we will select the polysilicon domains. So the polysilicon domains are the resonator domains plus the drive electrode. So you'll select this middle domain here, the other two domains that were associated with the resonator, and the drive electrode domain here. So basically 4 domains, 5, 6, 8, 9. Again, selection is two-step process, click and then right-click. Now we would like to assign air around this resonator, so I'll right-click on the materials, choose Open Material Browser, and this time expand the folder called Built-in. The first material would be air, so we'll right-click on air and choose Add Material to Model. I'm going to do one change here, which is I should have assigned air before I assigned polysilicon, but I didn't do so. So I'll move this air before polysilicon by just clicking on it and then dragging it up there. So I changed the order of the materials just so that I don't have to specifically look for domains that correspond to air. So I'll explain that, how that works. So first, you have air here first within the materials branch. And in the geometric entity level, you have domain by default. For selection, you will choose all domains. Obviously, the question is, well, all domains are not air, so why would I choose all domains? The idea is I choose all domains and then override the domains which are not air. So I've already overridden 4 domains here which are not air by saying these are made of polysilicon. I'll continue to do so till I assign all other material properties. So I have air, I have polysilicon. Now I will choose silicon nitride. So I'll right-click on Materials, choose Open Material Browser again, expand the MEMS folder, and then this time expand the Insulators folder. And then choose silicon nitride by right-clicking on it, and then choosing Add Material to Model. The second time when you add a material, this selection box will be empty. So you will have to specifically assign the material. So this time we are going to choose this domain here that is beneath the polysilicon material, shown in pink right now. So I'll click on it, then right-click anywhere on the graphic screen. And finally, the last material, which is the substrate, silicon oxide, I'll assign that. So I'll right-click on materials one last time, choose Open Material Browser, expand the MEMS folder, expand Insulators folder, and then right-click on silicon oxide and choose Add Material to Model. So that's the bottommost domain. So I will click on the domain and then assign it. So that's silicon oxide. So automatically, air will be assigned to only the material properties which are not, to domains which are not overridden by the rest of the materials below it. Okay, so here's electromechanics interface. The first thing we need to do here is we need to assign what is linear elastic dielectric here. So in what domains are we going to do both electrical calculations and solid mechanics calculations together? Those domains only correspond to the resonator. We have already made a selection of the resonator, so we'll click on this selections menu here and choose resonator. The other solid domains, that is the drive electrode, silicon nitride, silicon oxide, we'll assume they are perfectly rigid. So if they are rigid, we don't need to do solid mechanics calculation on it. Obviously, you can do the solid mechanics calculation on it, but to save time, we will assume they're rigid. So we don't need to do the solid mechanics calculation on them. But since they're not moving, we need to tell Comsol that they're not going to move. They're solid, but they're not going to move. And to do so, we'll right-click on electromechanics and choose a condition called fixed mesh. So all it does, it doesn't allow the mesh to move on those rigid objects. So you right-click on electromechanics, and then you will see the first option here called deformed mesh, one of the first few options called deformed mesh. And then we'll choose fixed mesh. And we are going to select the drive electrode, the silicon nitride, and silicon oxide. So those are all fixed. Now we'll apply boundary conditions. Boundary conditions, you have two physics here other than moving mesh. The first one is solid mechanics, the other one is electrostatics. So you need to apply boundary conditions for both the physics. So first we'll start with solid mechanics. The resonator is fixed on two of the boundaries, so we'll right-click on electromechanics and choose structural fixed constraint. So again, structural here and then fixed constraint. So click on it, and then we'll fix the bottom boundaries of this polysilicon resonator. So this boundary and this boundary, so that you see the numbers 18 and 60. Again, the process of selecting these boundaries is two-step. First, click on that boundary, then right-click anywhere on the graphic screen. Same with the second boundary. That is all the structural mechanics boundary conditions that you need. Now moving on to the electrical boundary conditions. So it has ground boundaries that are grounded and some boundaries that are subjected to electrical potential. So we'll right-click on electromechanics and choose electrical and then choose ground. And then select the bottommost two boundaries here, the base of silicon oxide. That boundary here, that boundary there. We have few more boundaries that are grounded. We will choose them by, again, adding another ground feature. So we'll right-click on electromechanics, choose electrical, choose ground again. We are describing a second set of ground boundaries. And then in the second ground feature, or the boundary condition, from the selection list here, we will choose resonator boundaries. So it's a selection we have already made. Finally, we'll specify where is the electrical potential. So we'll right-click on electromechanics, choose electrical, and choose electric potential. And for electric potential, we'll make the selection to be drive electrode boundaries. And here for electrical potential, we'll type down the parameter that we already defined, capital V, small dc. That's basically 35 volts. We can work with the default mesh here, but I'll just refine a bit. Let's first build a mesh, the default mesh. Now, right now, you'll see the mesh looks pretty different than what you would expect. That's because we have turned off the preserve aspect ratio. So if I go back here to view one axis and turn it back again on, choose the apply, it looks better. But if you zoom in here, you'll see that the gap between the resonator and the nitride, silicon nitride, they have almost just one element across the gap. So you need more elements across the gap. To do that, we'll right-click on Mesh 1 and choose Free Triangular. So free triangular means we are going to put triangular elements on this geometry, which we already have, but we want more control over the element size. So we are manually defining the element type, free triangular. And then we go to the size option just above the free triangular that shows up when you choose the particular element type, and then change the element size from predefined to custom. Here there are several options for defining the element size. I'm not going through all these options here. I can discuss this later on if you have any questions. But in the last option which says resolution of narrow regions, I'm going to type down 1.4. So what does that mean? Resolution to narrow regions means in the narrow regions put more elements than it was before. So narrow region are the gaps. Gaps are narrow, so I want to put more elements there. So then I click on build all. So now you'll see or observe that at least looks denser than before. It has put more elements in the narrower regions. The final step here is to just right-click on study 1 and choose compute, because we have set up the physics, we have set up the mesh and the boundary conditions and the material properties. So by computing, we want to calculate the distribution of electrical potential, and we also want to calculate the displacement of the linear elastic dielectric. So a plot that we are seeing right now, if I zoom in here, shows you the distribution of the electrical potential between ground and the drive electrode. The displacement plot here, the default displacement plot shows you x displacement, but if you want to plot the y displacement or total displacement, you have to expand the displacement plot group, click on surface 1, and then click on this replace expression option here, and then look for displacement. So you have displacement, displacement field. Let's say I want to plot total displacement in the y direction or the displacement in the y direction. Then you would first choose electromechanics, then you would choose displacement, then you would choose displacement field, and then displacement field component in the y direction. Or if you already knew the name of the variable, you could just type in small v here without going through the process. And then click plot. So that shows you the displacement field in the y direction. It will bend slightly in the negative y direction or downwards towards the drive electrode. So that's just a static analysis, a DC analysis. What we want to do from here is calculate the pull-in voltage, meaning if I keep increasing, so if I keep increasing the voltage, the displacement will keep increasing. At a certain voltage, the structure will become unstable. I would like to know that voltage, and that's called the pull-in voltage. The method to get to that voltage is shown in this slide. So in the previous problem, we were applying a potential difference, calculating displacement. But what we'll do now is do the reverse. We will tell Comsol that I want this much displacement. Tell me what is the voltage required for that much displacement. So that's called inverse, sort of inverse modeling. I will tell you what is the displacement, give me the voltage required for that displacement. So in this particular case, we'll describe the displacement of a particular point on the beam, so shown by this red dot in this figure here. So we'll tell Comsol this particular point is displaced or has its y coordinate equal to this much. Tell me the electrical potential required for this amount of displacement. To be able to specify the displacement of a point, we'll go through 2 steps. It's called integration coupling. So we'll define an operator called integration coupling operator. All it does is takes a particular point and records the y-coordinate or whatever value associated with that particular point. And then we'll set that y-coordinate of that point to a variable name. Here I'm calling it y set. So I'm saying the y-coordinate at this point is equal to y set, which is what I'll specify. I'll specify how much is y set. And then I'll parameterize the y set so that I'll solve for a range of values of this y-coordinate of this point. So I'll move it down. So it's flat right now. I keep moving the point down, 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 down. And I'll keep calculating the voltage required for the displacement of this point. If you keep doing that, you will ultimately get a curve of applied voltage versus the displacement of that point. And from that curve, we can figure out what is the pull-in voltage or the voltage at which this beam will become unstable. So that process here requires me to first define that operator that will get me the y-coordinate of the particular point. We'll go back to this view 1 axis and then uncheck this preserve aspect ratio so that the geometry is easier to work with. And then we'll right-click on definitions, select model couplings, select integration. Now integration, the word itself, it may sound very weird or strange because we're not integrating anything. This is just a way to take the particular value associated with the geometry and make it global. Because if you integrate anything, what do you get out of it? You get out a scalar quantity which is global quantity. It has lost all its association with respect to the particular geometry or the physics, regardless of it. So we are just using this integration over a point to make that particular value a global value. And I'll tell you why I may want to make it a global value in about a few steps. So when I choose integration here, I'll choose the geometric entity level to point. And then we'll select this bottom point of this MEMS resonator that deflects, that actually goes down. So I'll click on it and then right-click anywhere on the graphic screen. You should see the point number 38. Now I'll define this parameter y set that I was talking about in this slide. This is basically the value that I want the y-coordinate to be equal to. So I'll right-click on global definitions, or actually we already have parameters on the global definitions. So expand global definitions, click on parameters, and then here we'll define another variable. I will bring the magnifier up here so you can see what I'm typing. I'll define another parameter, y set, small y, set. And then here I'll type in initial value for that parameter. It's 100 nanometers, so 100 within square brackets, small n, small m, as in nanometers. So that's the y set. I will need this magnifier still, so I'm keeping it here. Now what I need to do is set this here, this equation. The equation says int op 1 y equal to y set. Basically all it means is that y-coordinate of that particular point is equal to the parameter that I'm supplying. That's a global equation that I want to provide to the model. By providing a global equation, I want to back calculate the applied potential. So it's like I want to calculate potential, but I need to provide another equation or another. To calculate an unknown, I need to provide another set of equation, and that's the equation here is that the y-coordinate is equal to some value. So I need to add a global equation, and that we'll do by clicking on this option called show. The show is used for a variety of reasons. Right now we are going to use it to enable something called advanced physics. This advanced physics allows me to couple a finite element model with a global constraint. So I can apply any global constraint, not just specific one, any global constraint and solve it in a coupled way with the finite element model. So I'll click on advanced physics, then right-click on electromechanics, and then choose global equation. So one more time, right-click on electromechanics, choose global equations. In global equations, I'll type down the equation that I want to solve for. And the equation I want to solve for is basically that the integral of the y-coordinate over the point is equal to a parameter name. Integral of the y-coordinate of the point is equal to the y-coordinate of the point. But still, we have to go through this process. So we'll type down the integral of the y-coordinate over a point, which is given by INTOP1. So what is that INTOP1? That is the integral operator name. How do I know that? If I go back to the integration that I have defined here, you'll see the operator name is by default INTOP1. You can change that if you want, but I'm keeping it to default. And I go back to my global equations. So INTOP1 within simple brackets, small y. That basically tells you what is the y-coordinate of that particular point. That's all that means. Minus y set, small y set. So y set is the y-coordinate that I will set. So I want the whole thing to be equal to 0. So that's my equation. But I'll scale this equation. I'll scale the entire equation by y set. So that, let me expand this so I can look at the whole equation. So it looks like this. It still means the same because the whole expression is equal to 0. The only reason I have scaled it because I want to make it numerically easier. All these displacements are of the order of 10 power minus 6, 10 power minus 9. So if you're adding a global constraint which has all these variables of the order of 10 power minus 9, along with a few other equations which have different order magnitude, then it can be numerically difficult convergence-wise. So I'm making it easier by scaling the equation so that all magnitudes. Internally, Comsol will scale the finite element model so that the magnitudes of dependent variables correspond to almost 1 by scaling, internal scaling, just for convergence reasons. So I scale this. It still has the same meaning, which is the y-coordinate should equal to the set y value. In the name column, I need to type down what do I want to get out of this. So I'll define a variable here. I'll call it capital V small dc, which was the original variable name. But I'll add a few more letters to it. SP as in specified, capital S, capital P. You can use any name that you want. So what does that mean? I want to calculate the voltage that will make this equation equal to 0. Where is this voltage being applied? This voltage is being applied to this electric potential boundary condition. So I need to change this electric potential to capital V dc SP. So in summary, I don't know the voltage required to drive this electrode, and I have specified this as an unknown. I call this unknown capital V dc SP, or specified DC voltage. I don't know this voltage, but I do know the equation, a global constraint, that is the y-coordinate of that particular point has to be equal to the y-coordinate I want it to be. So I will calculate this unknown. So these two changes are needed here to calculate that. Now what do we want to do? I'll get rid of this magnifier. So as I said earlier, what I want to solve is for a range of values of the y-coordinate of this particular point. So that it slowly starts bending from horizontal and it keeps moving downward. So I'll keep increasing the y-coordinate value. To do that, you have to do something called parametric sweep. So you will enable an option called continuation, choose this add button, and then choose this variable y set. And we want this y set to assume different values. And I would like Comsol to solve for each value of y set and give me the corresponding electrical voltage so that I can make a plot. Okay, so the final step here is to specify a range of these y set values so that Comsol can solve for each of them. You do that by choosing continuation, choosing the parameter, continuation parameter as y set. And then here you specify a range of values that you can do by clicking on this button called range. And here you will provide a starting value. I'll put 140 nanometers within square bracket. Step by minus 2 nanometers within square bracket. Why minus 2? Because the y-coordinate will be decreasing as the beam bends, right? So I'm stepping with negative values. And then end at 120 nanometers. So theoretically, we know that if it was a 1D lumped linear model, then at 1/3 of the gap, you would reach the potential required for making this resonator become unstable. So we're using that as a guess to sweep across the values, meaning you decide on how many values do you want to sweep across, and till what values do you want to sweep across. So I've chosen the y coordinates going from 140 nanometers to 120 nanometers, hoping that within this range it will collapse, or I'll get the pull-in voltage. And one final modification you have to make here is in the solver settings here. So this is a very highly nonlinear problem. I've coupled the global ODE to find out the unknown, which is the applied potential, which is what I'm solving for. So we'll expand this stationary solver one and click on fully coupled one. This section here describes or decides how the nonlinear solver behaves. How do you solve the nonlinear part of the problem? So there are various methods, Newton-Raphson schemes. Within Newton-Raphson schemes, there are modified Newton-Raphson schemes. And one of them is called automatic highly nonlinear Newton-Raphson scheme. So it's used for highly nonlinear problems like this one. And that should be about it. And now I can right-click on Study and choose Compute. So now it will start solving the model for each value of y set. So for each value of the y coordinate, it will give me a corresponding applied potential, so that finally I can make a plot which will determine what is the pull-in voltage. So while that takes I think a minute or so, I will move on to the next slide, which shows what that plot should look like. So this is a plot of the unknown voltage versus that y coordinate. So if I start from this left-hand side, where I have the number 0.14 microns, so 140 nanometers here. If I keep decreasing the value of y coordinates so that you go closer to 0.11 here, the applied potential keeps increasing. So I keep increasing the y coordinate, the applied potential keeps increasing until one particular point, beyond which if I keep decreasing the y coordinate, the applied potential required for that keeps decreasing. So this is the maxima of this particular curve, applied voltage and applied displacement or applied y coordinate. That particular point corresponds to the pull-in voltage, meaning that if you were to physically, when you in your device, if you were to apply this particular potential, anything beyond this potential would cause the resonator to collapse. So you are at an unstable state. You cannot really solve for stationary problem. Stationary problem meaning steady state equilibrium. You cannot have equilibrium beyond this particular potential. So that's why you don't really solve for an increasing potential that solve for this potential small value and then keep increasing it, keep increasing. You don't solve for it because at the point you will hit the pull-in voltage beyond which you can't solve for because it's unstable as a steady state problem. You can solve it as a transient problem, but not as a steady state problem. In this manner, we will get, so here we have the computer solution. Now I'll right click on this results to get a 1D plot of that unknown voltage versus the y coordinate. So I'll right click on 1D plot group, or click on 1D plot group by right clicking on results. Right click on 1D plot group and choose global because I'm plotting a global variable, a global parameter. And in the global parameter, we'll just type down in the expression column, we'll just type down the unknown that we were trying to calculate. That was capital V, D, C, capital S, P. Basically, the unknown potential. And then take its absolute value. So we'll take the absolute value of potential. So we'll type, I'll use the magnifier again, ABS. Absolute value. Why am I taking the absolute value? It's more mathematical than anything to do with physical sense here. So when you calculate electromagnetic forces, it depends on the gradient of V squared. So that means the solution for that is either plus or minus mathematically. So when you back calculate the potential, it can return you negative magnitudes of potential as well. So we're not worried about the negative magnitudes of the potential, but it will still have the same physical effect. It's just the magnitude will be negative or positive, doesn't matter. Mathematics as far as mathematics is concerned here. So I'll take the absolute value here and click the plot sign. And now remove this magnifier. So here we have the plot. I didn't sweep it all the way, beyond this maxima on the left-hand side, but you can see you have a maxima here, and if I zoom in here, it's approximately 59.62 something volts, and the y-coordinate should be 12.6. 12.6 for the y-coordinate. So that means if I take this particular model and in the steady state I apply a potential beyond 59.6, let's say 60 volts, this will not solve because you have reached an unstable state beyond 59.6. If you apply something below 59.6, it will solve. So that it's okay. So then it's another check that it is the pull-in voltage. I'll talk later about how you can get a transient response where you can get a full collapse of the beam. Finally, and a rather quicker one is frequency response of this kind of problem. How do you model frequency response? So for frequency response, we will disable this global equation. We no longer need to do this global equation because we have a fixed known DC bias. We'll use the original DC bias, capital V DC. But we would also like to apply a harmonic perturbation, an AC perturbation on top of the DC bias. To apply a perturbation, you will right-click on electrical potential and choose harmonic perturbation. And here you will put in 0.1 volts. So 35 volts plus 0.1 times sine omega t. That would be the mathematical expression for applied potential. And we will also add some damping to this model. So if you knew the amount of damping, in this case I'm adding it explicitly. So if you knew the damping in this linear elastic solid, you can right-click on it and choose damping. And here there are two types of damping available, loss factor damping and Rayleigh damping. By using the Rayleigh damping, I'm putting in some parameters taken from literature. 4189 is the value of the first alpha. You must be familiar with Rayleigh damping from some courses in graduate school or undergraduate classes. 8.29 E minus 13 value for beta. So I'll use the magnifier again. So for alpha, I typed down 4189 hertz. For beta I typed 8.29 E minus 13. Usually, so how do you get these values? Well, it's not that easy. Usually you have to find out the critical damping ratio, which is available in literature for two particular frequencies. Knowing the critical damping ratio and knowing the two frequencies, you can back calculate the values of these parameters, alpha and beta. Usually you don't get directly in literature that here is alpha, here is beta. You'll have to calculate those parameters. And the final thing is the study, the analysis. We no longer want to do a steady state analysis. We want to do a frequency response type of analysis with a DC bias. So we'll right click on this topmost branch called root to add a different type of study. So we'll choose add study. And then we'll choose a second option here, pre-stressed frequency domain. So click on it and then click finish. So what does this do? First it solves for the stationary problem, which it will solve for just the DC bias. And then it will add a frequency domain perturbation. So it will solve for the AC problem, which is the harmonic perturbation of applied 0.1 volts. But here you have to specify how many frequencies do you want to sweep across. So we'll type down a range of frequencies. And I'll use the magnifier again to show what I'm typing. RANGE. This is the internal function you can use to type down where to start from, how much to step with, and where to end. So we're going to start from 7.65 megahertz, step 0.01 megahertz, and then end at 8 megahertz. And that's about it. And that should be okay. And then you right click on study, choose compute, get rid of this magnifier. And this should be quicker than a stationary problem. Usually all the stationary problem will be more time consuming than a frequency response type of problem, because frequency response is linear whereas a stationary problem can be nonlinear. While it does that, what are some of the applications of this electromechanics? Well, applications come in designing sensors like capacitive pressure sensors, accelerometers, MEMS oscillators, comb drives, parallel plate actuators, and other capacitive devices. So two pictures on the right-hand side are showing, the first picture is showing the electromechanical actuation of a comb drive. And the second picture is showing the thin film damping or squeeze film damping in an accelerometer. So you're basically solving for the vibration of an accelerometer, but there is damping associated with a thin film of gas on top of that accelerometer. And that damping is modeled using a thin film flow interface. Going back to the model, we'll right-click to create a plot. So I'll right-click on results, choose 1D plot group. And I'm going a bit fast here, so it would be difficult to follow me if you were following. So you'd have to stop at this point here. So I'll right-click on 1D plot group and then choose point graph, because I want to trace the displacement of the particular point I was using. So I'll select that particular point again, and let's plot the y displacement of that point. So I type small v for y displacement, and then I click on plot. So this is the frequency response. What you're seeing is anti-resonance and resonance frequency response of the particular point there. So in this case, you can clearly separate the anti-resonance and resonance frequencies, which are close by though. So this tells you how you would do a frequency response analysis with a DC bias. Just same way you can do an eigenfrequency analysis with a DC bias, which will tell you how much the resonance frequency will shift because you have a DC bias. Okay, now that set of examples is complete, so I'll move on to other features. Solid mechanics within the MEMS module. Solid mechanics within the MEMS module has all the other features that the electromechanics itself has, except that it has a few other features. One of them is to calculate effective mass and spring constants of a structure. So it's getting the lumped parameter out of a structure. This is available only for solid mechanics calculations. You can do frequency response type analysis without having a pre-stress. So you don't necessarily need to pre-stress some object to get frequency response or resonance frequencies. That is a concept only in electromechanics, but not in solid mechanics. Of course, you can also get eigenfrequencies and frequency response if the structure is already stressed. And finally, you also have two different types of studies called modal type of studies, which allow you to model or solve a problem in a reduced manner, meaning you don't have to solve for the full transient response of a structure. You don't have to solve for the full frequency response of a structure because it takes too much time. Instead, you can solve a reduced problem which takes into account a certain number of eigenmodes around the mode that you're concerned with or exciting the structure with. Damping options. So there are various damping options here. We already looked at loss factor damping, Rayleigh damping. Then I mentioned already about fluid structure interaction, thin film flow for modeling losses due to fluid interacting with a solid. Thermoelasticity, this is the damping associated or loss associated with heat conduction due to a structure that is locally expanding and contracting. Electrical features, you can do just electrostatics and just electric currents conservation in the MEMS module. So solving conservation of electric currents or electrostatics, modeling basically conductive metals or fluids or dielectrics is done by these interfaces, electric currents, electrostatics, and also electric circuit, which is I'll show you in the next slide. The two figures here at the bottom of the slide show two particular boundary conditions in these interfaces that allow you to model a very thin conductive layer and a very thin dielectric layer with very high permittivity. These boundary conditions allow you to not specifically model the thickness because they're very thin. If you model the thickness, you will have problems with meshing the very thin elements and then a lot of mesh elements and increased computational time. Instead, any thin layer can be modeled with specific boundary conditions. And it almost exists for any physics, not just this particular physics. Electrical circuit, you can create your own electrical circuit within the Comsol, the MEMS module, or you can couple it with the finite element model. RF MEMS, this will be a new example or a new model library example in version 4.4 that will show you how to calculate the transient response of a MEMS switch. So in this example, you'll be able to calculate the displacement and the increase in capacitance of a device when the solid or the resonator collapses fully. And that we do by making some concessions. That is, you have to model the contact in a rather approximate way called the Hertzian contact. But this will be available in a couple of months with 4.4. So that will have a variety of applications in other areas related to RF switches as well. Thermal MEMS, that means the MEMS module has interfaces to calculate thermal stresses, either due to uniform temperature rise or due to non-uniform temperature rise, or due to electrical heating known as Joule heating. So you can couple various interfaces to get the thermal stresses due to any heating mechanism. All right, we'll take a short break before moving to the next topic. This is the last topic, but I'll do a demonstration of piezoelectric devices, how to set up a frequency response and get the impedance plot for a piezoelectric device. So let's say 5 to 10 minutes. So start with the piezoelectric effect, which seems to be another important field in MEMS modeling. Piezoelectric effect, piezo means pressure, and it's found in piezoelectric crystals. The effect basically means either, say, you apply mechanical load and you can convert it to electrical charge or voltage distribution, or you apply electrical potential difference and you convert it to mechanical stresses within the piezoelectric crystal. So they are called direct effect and inverse effect. So you can model both in Comsol. The direct effect, where you calculate the mechanical load given the electrical load, or you calculate the electrical load given the mechanical load, direct and inverse. There are 23 piezoelectric materials within Comsol. Some of the common ones are quartz, PZT, PVDF, and some typical applications are listed here: sonar transducers, print heads, acoustic devices. The first one is actually the first practical application, sonar transducer of piezoelectric devices during World War I. The figures on the right-hand side, the two figures, one of them is showing the shear mode of a 80-cut quartz crystal. And that's something we will do. I set up a simple model to show how to model the resonance mode of a 80-cut quartz piezoelectric crystal and what is important in that modeling. The second example here shows how to model direct and inverse effects in a piezoelectric crystal. In this case, the piezoelectric crystal is radially polarized, so you have to set up a local coordinate system to account for different polarization than what is available for the default material properties within the materials branch of Comsol. So all these two examples and others are in Comsol's model library. In Comsol, you have two forms, stress charge and strain charge, to relate the constitutive laws, the mechanical and electrical laws. The stress charge form relates stress to strain and electrical field, and then you have the electrical displacement field relate to stress and electrical field. In strain charge form, you relate strain to stress and electrical field. They will both give you the same result. The difference is in how you provide the material properties. Each will require a different form of the material property. So you can, if you have properties related to either direct or either the stress charge or strain charge form, you can directly use those properties. In Comsol, the material properties that are available for all the piezoelectric crystals, they're available for both stress charge form and strain charge form. Interface, the interface that solves for piezoelectric devices or materials is called the piezoelectric devices interface. It can be a 2D simulation or it can be a 3D simulation. It can be a static simulation, or it can be a eigenfrequency simulation. It can be a damped eigenfrequency simulation. That means you can have a damping, transient, and frequency response simulation. The important thing in modeling piezoelectric crystal that you have to keep in mind, just for piezoelectrics, is to know the orientation of the crystal, or to define the material polarization. If that is not correct, your entire the results will be shifted, or it will be wrong, basically. So this one thing can change your results drastically if it is not correct. So this means you have to really define the material polarization. In Comsol, all the default material polarization is with respect to the positive z direction. The properties are defined like that. So if your material is polarized in a different direction, you need to define a separate coordinate system, a local coordinate system, that will rotate that default coordinate system in Comsol and polarize or calculate the equivalent properties in the rotated direction. So I'll show you an example where this needs to be done. This shows you what is needed to model a piezoelectric device. And as you need the geometry, material properties, the material orientation, which is the most important, coupling with other physics. It could be coupled to other physics as well, boundary conditions, and analysis type. So analysis type, the green arrow shows you the amount of time taken by the analysis in increasing order. So the time response will take you the most amount of time, whereas a linear analysis like frequency response or eigenfrequency analysis will take you lesser time. This is a snapshot or screenshot of all the piezoelectric materials within Comsol. A related concept to piezoelectricity is piezoresistivity, where piezoresistivity is found in most semiconductors, where you apply a stress and it leads to change in resistivity, or you apply a strain and it leads to change in resistivity. But it's only one-way coupling, unlike piezoelectricity, where it is bidirectional coupling between the electrical and the mechanical problem. Here it's only one-way coupling. The applied stress leads to change in resistivity. It doesn't go the other way around. This can also be, there's a separate interface for modeling this kind of effect. And we'll right away go into the model. This will be simpler to build because of simpler geometry. What we want to model is the thickness shear mode of a quartz oscillator. I think I keep pressing this button. Yeah. What we want to model is the thickness shear mode of the quartz oscillator. And for that, we need to specify what is the material property, what is the material orientation, and if you want to do eigenfrequency analysis, you will find the eigenfrequency response analysis to find the particular mode, the shear mode, and then do a frequency response analysis. In the full, this particular example is taken from a model library. In the model library, the example model actually couples this piezoelectric device to electrical circuit. So you can drive the piezoelectric device with an electrical circuit. In the example model, electrical circuit consists of a capacitor and a voltage source. So you can see the effect of changing the capacitance on the resonance frequencies of the piezoelectric device. What we are going to set up is a cut-down version of it, where we are not dealing with the electrical circuit part of it, but the piezoelectric finite element model itself. But if you were interested in the full model, you would click on View, click on Model Library, and then expand the MEMS module folder, expand the piezoelectric devices folder, and then click on this thickness shear quartz oscillator. So if you click on Open PDF, it will go through the entire documentation about setting material properties and material orientation, and also coupling with electrical circuit. So I'll go through the basics of that model. So our steps are as shown in the slide. We draw the geometry, which is pretty simple. It's just a cylindrical crystal. Study type, we are doing a frequency response analysis. Material properties, the quartz crystal. Material orientation, this is something you have to be very careful about and define a local coordinate system, usually provided by the supplier. You can get from the supplier the Euler angles for the particular cut. For example, this is an 80 cut quartz crystal. So there are Euler angles associated with it, which will tell you how the what is the direction of the material polarization. Boundary conditions, and then finally getting from this analysis, what we want to get is an impedance plot, that is impedance versus frequency. So we'll draw the geometry. Geometry is pretty simple. We just click on New and choose 3D after clicking on New. But I've loaded an example file with a lot of post-processing, so I have to get out of it first. Click on 3D, click on Next, and then the piezoelectric device interface is in the structural mechanics folder. So if you expand the structural mechanics, you will see piezoelectric devices here at the bottom, one of the bottom interfaces. So click on it, then click on the blue arrow called Next. And we'll do a frequency domain analysis, so we'll select the second study type, frequency domain. And then click on Finish. The geometry scale here is in millimeters. Ideally, it would be a bit more than millimeters, but we'll do away with millimeters. So we'll change this default length unit from meter to millimeters. And we'll draw the geometry, which is basically a cylinder. So you'll right-click on Geometry 1 and choose Cylinder. The radius here is 0.835 millimeters. So 0.835. So the radius is 0.835. The height is 0.334. 0.334. So I'll put a magnifier just to show what is the radius and height. 0.835, 0.334. And the axis type here is y-axis. So we'll change this axis type to y-axis. And this is important because, so let's click on Build. So when you choose the axis type, what happens here? When you choose the axis type as y-axis, the thickness of the cylinder here, the vertical thickness, is along the y-axis. And this is important because you're going to define a local coordinate system. And the local coordinate system is defined with respect to, for the 80 cut quartz crystal, is defined assuming that the crystal thickness is in the y direction. And if it is in the y direction, and then you have certain Euler angles which you will use to rotate that crystals. But it starts from its thickness along the y direction. So if you orient it in such a way that the thickness is in the z-axis and you use those Euler angles, your results will not be correct. You can, however, still do the modeling with the thickness in the z direction. In that case, you'll have to change the Euler angles provided by the supplier in a way that makes sense. And that is described in the model library example model, how you would begin the simulation if the thickness was not in the y direction but in the z direction. So here we have quartz as a material. So we'll right click on materials and choose Open Material Browser and expand the piezoelectric branch and look for quartz. So if you find quartz, right click on quartz and choose Add Material to Model. So one more time, you would right click on materials, choose Open Material Browser, expand the piezoelectric folder, and then look for quartz. So you would right click on quartz and choose Add Material to Model. Now the important part, which is defining the Euler angles. So here you have to define a local coordinate system for which the Euler angles are given by 0, 35.25 degrees, and then again 0. These represent basically rotations about the z-axis, and then about the x-axis, and then about the z-axis again. In this case, there is only a rotation about the x-axis, which is 35.25. So we'll define that local coordinate system by right-clicking on Definitions, choosing Coordinate Systems, choosing Rotated System. And I'll put the magnifier again. And for beta here, we'll put in a value. For alpha, leave the value to 0. For beta, we'll put in a value 35.25. and within square brackets DEG, as in degrees. So this is a internal variable name for degrees in Comsol. And leave the gamma to be 0. Get rid of this magnifier. Now we need to change the coordinate system here in the material model. So if you expand this piezoelectric devices, underneath that there is piezoelectric material 1. Here's where you specify the coordinate system. By default is the global coordinate system, which is shown by this blue arrow in the graphic screen, Z, green arrow is Y, and the red arrow is X. We don't want to use that, so we'll change it from global to rotated. So we are using the coordinate system, which specifies the Euler angle that defines the crystal orientation. Now comes the boundary conditions. So having made that change, we need to define the boundary conditions. The boundary condition here is that the top is grounded. So we'll right-click on piezoelectric devices, choose electrical, and choose ground. And after you choose ground, you select the topmost surface by clicking on the surface and then right-click anywhere on the graphic screen. The bottom has electrical potential, so you will right-click on piezoelectric devices, choose electrical, choose electric potential. Now, instead of electric potential, we will choose terminal. Sorry. The reason I want to choose terminal is because we want to calculate lumped parameter like impedance. If I choose electric potential, it will not calculate impedance. It will do all the physics that is required, but it will not calculate impedance. So instead, I'll use this special boundary condition called terminal, which allows Comsol to calculate lumped parameters. Depending on the model, it calculates capacitance, impedance, resistance, and so on. In this model, impedance would be of interest. So I'll choose terminal instead. Terminal. And I'll assign this terminal boundary condition to the bottom boundary here, which is the thickness bottom boundary. So click, and then right-click anywhere on the graphic screen. Two-step process. First click on it, then right-click anywhere on the graphic screen. I'll change the terminal type to voltage. And here I'll put in electric potential, let's say 10 volts. So I'll use a magnifier again. So I change the electric potential to 10 volts. I will get rid of the magnifier. And one last thing we'll do is introduce some damping here. Ideally, you should be able to find the damping coefficients for loss factor damping, for example, from literature. Here I'm going to use the isotropic loss factor. So I'll right-click on piezoelectric material, choose damping and loss. So this is explicit damping. And after choosing damping and loss, we'll change the damping type to isotropic loss factor. So change the damping type by clicking on the option and changing it to isotropic loss factor. And then in the option next or below it, which says isotropic structure loss factor, we will choose the option user defined, as I'm showing right now. And for the value, we'll type in 1e minus 3. So here we go, 1e minus 3. In a typical device, though, you will find a whole matrix. It won't be an isotropic value, but it will be a whole matrix that you will get. And in that case, you will have to use loss factor for CE. Either you do it user defined here, and then change it to symmetric and enter all the loss factor values here, because it won't be a single value, an isotropic. But for now, we're just using a single value isotropic loss factor. And get rid of this magnifier. Now comes the mesh. Now we're more concerned with the shear mode, so the on-plane surface mode. So it's necessary that we resolve that mode on the surface. And to do that, you can use triangular mesh. However, you don't need to use triangular mesh all the way through the thickness of it. And these can be of high aspect ratio, these geometries. So we will use swept mesh on this, but we will modify the default swept mesh. So we'll right click on mesh 1 and we'll choose swept. Then if you click build all button, you'll see it has created these hexahedral elements. So it's basically a quad element extruded in the thickness direction. But since we want to resolve the shear mode on the surface, we don't want a quad mesh there. We would rather have a triangular mesh there, because that has the ability to resolve the waves better than this quad mesh. So we'll change this element type here. In the settings of swept 1, we'll expand this sweep method. And in the sweep method, instead of this generate hexahedrons, we'll click on that and change it to generate prisms, or in other words, generate prismatic elements. Then click on build all. And the thickness direction, let's use more than 2 elements. So we'll right click on this swept 1 and choose distribution. This will help us use a bit more than 2 elements. So let's say 4 elements. So right click on swept 1, choose distribution, and for the number of elements, I'll type down 4. And then click on build all. So that sets up the prismatic elements of this geometry. You have to be very careful that the element size in plane, that is in the XZ plane, should be good enough to resolve the shear waves that will occur in this. If it's not good enough, that means you'll have to go and change the element size here and make it smaller. So for 3 dimensions, we recommend that you have at least 5 elements per wavelength. So accordingly, depending on which wavelength you're interested in, you have to modify the mesh size. In this case, it turns out this is good enough for the shear mode that we're interested in. So in the frequency domain here study, we have to specify a range of frequencies. So we'll specify a range of frequencies there. Let's go here. So range of frequencies, we'll start with, we'll click on this range button. And for start, we'll type down 5.09 E6. So as in 5.09 E6 hertz. We'll step by 1000 hertz, so I'll type down for step 1 E3, 1000 hertz. We'll stop at 5.125 E6 hertz. Now you notice I have carefully, so when you first do such analysis, you will obviously not, and if you really have no idea about what frequency, what eigenfrequency you want to look at, you can't get these numbers right away. It's an iterative process. First thing you would have to do in this case is you would have to do eigenfrequency simulation. You do eigenfrequency simulations, and then you figure out what is the shear mode you're interested in. So you look at the plot and you see, okay, this is the shear mode that I'm looking for. So once you know the shear mode you're looking for, you get the eigenfrequency. Once you get the eigenfrequency, then you would like to sweep in and around that eigenfrequency. So I first did do a eigenfrequency simulation, and then I got the eigenfrequency, and then I'm sweeping around that eigenfrequency, and that's how I got these numbers. What about the stepping of the eigenfrequency? That's also something you have to be careful about. So you get the resonance frequency, then you want to sweep around that resonance frequency, but you have to be very careful about the step size you choose for stepping the eigenfrequency. You don't want to step too big. If you step too big, you'll completely miss the resonance spot, and you'll just see a response that linearly increases with frequencies. You won't see a regular frequency response curve. So the frequency stepping should be small enough. Now that is also again an iterative process. You don't know right away how much is a good amount if you don't have prior experience with this. So it would be an iterative process. You'll try out different stepping and you'll see, oh, nothing is happening. You're not seeing a frequency response plot. If you're just seeing a linear increase, that means something is wrong with that stepping. So we click on this replace, and then right click on study 1 and choose compute. Now that will take a couple of minutes, and while it does, I just want to elaborate a bit about the material properties. So the quartz material that we added, these are the material properties. So they are not, obviously they are not isotropic. It's a piezoelectric material. The elasticity matrix is an isotropic. Coupling matrix is an isotropic. Coupling matrix is that one that connects the electrical field with the stress, mechanical stress. And then the relative permittivity is also a diagonal matrix. So these are not just regular isotropic values. Now these matrices get rotated, and these values get changed because of the local coordinate system that we have defined. So we defined a local coordinate system with some Euler angles. So these properties will rotate, and they will have different properties, different values, because of the change in coordinate system. And that is what is important. So when you set up such a model, and if you think that you have done everything correct, this is one place to look. That is, you have to see whether your material polarization is correct. And to be able to figure out whether it's correct or not, you have to look at the rotated properties. So you calculate the rotated property. You can output the rotated properties of Comsol. You take the rotated properties and you compare that with any data that the supplier might have given or might be in any published literature. So if they don't match, that means something is wrong with the coordinate system. And this simulation is about to finish. So our goal here is to now plot the get the impedance, and in this case you'll have both real and imaginary values. If I hadn't put any damping, then I would only have imaginary values. But because I put damping, so I'm introducing losses, I'll have real values as well. So what I'm looking now here is just the shear mode of this piezoelectric crystal. Now you'll notice one thing though, I haven't used any mechanical constraints here. Mechanical constraints are not necessary in any frequency domain or eigenfrequency domain calculations as such. They are needed in stationary calculations. It's an absolute necessity in stationary calculations, but not for frequency domain or eigenfrequency calculation. But it is a good practice to use constraints in frequency domain calculations to eliminate vibration modes that you're not interested in. In this case, I already knew the frequency, so I already knew the response because I did eigenfrequency calculation earlier. So I already knew the response mechanism, so I did not think it's necessary to use any mechanical constraints. So what we're interested in is the impedance plot versus frequency. So for that, we'll do a 1D plot. We'll right-click on results, choose 1D plot group. And then right-click on 1D plot group and choose global. Because all the lumped parameters like capacitance, resistance, impedance, these are just global quantities. And in the replace expression option, click on the replace expression and choose piezoelectric devices. Okay, I keep saying impedance, admittance. And then choose admittance. And then now admittance will have both real and imaginary components. So we'll take, let's say, the absolute value. So A, B, S, and within simple brackets, you put in the variable name. So I'll use the magnifier to show what this should look like. So once you add the admittance, you will just have PZD dot capital Y 11, and you just add this absolute function that is ABS, simple bracket open, and then simple bracket closed. And then the plot. So that again shows you the resonance and the other mode associated with this piezoelectric crystal. Now you could have extended this model by going to this terminal 1, and instead of using a voltage source here, you could have changed it to a circuit. And after you change it to a circuit, you could add another electrical circuit here by right-clicking on model 1, choosing at physics, and then going into AC/DC, and then choosing electrical circuit interface. In the electrical circuit, you can add all these different lumped sources, like capacitors, resistors, voltage sources, or current sources. And this is how your model would be, this electrical circuit would be connected to the piezoelectric device model. A good example of that is in the particular example model I was talking about earlier. which is a thickness sheared quartz oscillator. If I open that model, you'll see it uses piezoelectric devices, and it also uses electrical circuit interface, which has a voltage source and a capacitor, and a feature here, external I terminal, that connects the electrical circuit to the finite element model through this terminal. So terminal number 1 is the one that connects both these physics interfaces. Okay. I'll just briefly go through some few other application examples. This first one is the one that's as a hands-on in that booklet that you must have, the Introduction to MEMS module. This is an example or a tutorial about a pressure sensor. So what you have here is a silicon die bonded to a metal plate. There is a diaphragm that has a sealed air chamber, and the external pressure on the diaphragm increases, leading to the deformation of the diaphragm, which causes a decrease in the gap, air gap, which causes a change in capacitance. So that's why it's a pressure sensor. If the pressure increases or decreases, the capacitance changes. So it senses the pressure that way. So this particular example model shows you how to use the electromechanics interface to set up this pressure sensor. And then it also analyzes what happens if you have thermal stresses in the device. So when you are manufacturing the device, obviously it's done at particular operating temperature. And when it's cooled down at regular temperature, there will be thermal stresses. So you have to account for what change in capacitance will occur due to these thermal stresses. This other example model, also taken from the model library, is of electrostriction. This is another one where you can study the effect of the electrical field on the strain or the mechanical aspect of a material. This electrostriction generally occurs in all dielectrics. It's different from piezoelectric effect. Electrostriction is a quadratic effect. Piezoelectric effect is a linear effect. This example shows how to set up a gas sensor where you have a thin film encapsulating aluminum electrodes etched on a piezoelectric substrate, and you're interested in calculating the eigenfrequencies or resonance mode of the surface acoustic waves. So this model does the eigenfrequency analysis of such a device. The idea here is that as the film absorbs some chemicals, the mass increases, which needs to change in or shift in the eigenfrequency, and that's why it's a gas sensor. Fluid structure interaction, the first couple of pictures here are that of interaction between a solid and a thin film, as in bearings, like journal bearing, tilted pad bearing, step bearing, any bearing that you can think of. So you basically solve for Reynolds equation, that is fluid pressure on a surface. So you don't solve for Reynolds equation on a volume or on an area, but rather on a surface, because it is applicable to a very thin domain. So you obviously don't want to mesh a very thin domain and calculate everything. You rather use it as a partial differential equation on a surface. And then you couple the fluid pressure calculated from the Reynolds equation to structural mechanics, and that's fluid structure interaction in any bearing example. In this case, the example is that of a tilted pad bearing. The second example you must have seen in the morning session is fluid structure interaction. You have a fluid coming in from the left. It forces an obstacle and goes out the outlet. But the fluid stresses force the solid. So for the solid, the fluid stresses act as a boundary condition. However, when the solid deforms, the fluid domain also deforms, or the fluid domain changes. So you have to solve a coupled problem, fluid structural mechanics. If the structural mechanics were not affecting the fluid mechanics at all, then you would just solve a fluid mechanics, use the load from fluid mechanics, and calculate structural mechanics. It would be one-way coupled problem. But in this case, it is not so, because the fluid mechanics gets affected by structural mechanics or the deformation of the obstacle. So there's an interface for solving this type of problem as well, fluid structure interaction, in the MEMS module. This is an example of a vibrating micromirror, generally used in optical elements and medical imaging and heads-up displays. So you have a micro mirror which is vibrating. and you have air around it. Because of this vibration, there are losses associated with thermal and viscous layer that develops around that vibrating micromirror. You have to really resolve these thermal and viscous layers by by solving for the pressure acoustics around this micromirror, and we call it thermoacoustics. So all it does, it solves for linearized Navier-Stokes equation coupled with the continuity and energy equation that is also solves for temperature rise. So this is a coupled thermoacoustics shell interaction. So this is a case where the MEMS module alone would not be enough, because you have to couple this with shell interface in structural mechanics and also thermoacoustics, which is in the acoustics module. This is an example of heating circuit. So this is sort of a multi-scale model in that you have a electrical resistive layer deposited on a glass substrate. This resistive layer is shown in the blue shade here. You apply electrical potential to this resistive layer. It causes heating of this layer. The heat is transferred to the glass substrate, and the glass substrate heats up any incoming fluid. So the idea is to heat the fluid, but you want to keep that heater, the thin heater, away from the fluid, so you introduce a glass substrate in between. However, the more you heat, there are chances that it will delaminate, so there will be interfacial stresses because of heating. So the idea here is you have to study what is the temperature rise and what are the thermal stresses, both in the solid, the substrate, the glass substrate, and also on the shell. So you're doing Joule heating on a shell and coupling it with heating and structural mechanics of the glass, thick glass volume. So there are many other such examples that I have not shown or have not talked about, and you'll find them all if you click on View, and then click on Model Library, and then expand the MEMS module. And here, if you expand each of these folders, so the first folder, actuator, has these resonator models that I was doing earlier, step by step. So there are 2D models, basic, frequency domain, pull-in. If you missed any step, or if you did miss most steps, because it might be going fast, then you would have to, you can go here and click on the open PDF document to take a look at the step-by-step instruction to build the same model that I was building. So it will go through an explanation, a summary, and the step-by-step instruction to build those models. Next to the 2D models, then there is a similar 3D actuator model. So once you start off with the 2D model, then you can continue with the 3D electromechanics actuator model. It has similar analysis, but on a totally different geometry, but same DC bias, pull-in, and so on. And then there are other example models with related to other areas. There are some example models that are not included in this model library, but they can be found on our website. So when you first install Comsol, these examples won't show up. So you would have to update Comsol model library by enabling some option here in options preferences. By default, it should already be on. That is, it should already be looking for model library update. For example, here it starts looking, but because I'm not connected to internet, it won't be able to download those examples. But by default, you should be able to check for the model library update by clicking on this button here, model library update. So if you click on model library update and you're connected to internet, then all the models that are newly added but not included in the installation will show up, and then you can download them. It takes quite a bit of time, so make sure you have sufficient amount of time left to download all the model library examples that are not included in the model library here. Okay, so I'll stop talking now, and I will I will point you now to the hands-on example of the pressure sensor. So this is a great example. It has a 3D geometry, and it guides you through several aspects: the electromechanics interface, thermal stress calculation, structured mesh